Hello and welcome to my channel, Vision Basic. My name is Dennis Osborne. This is my first video on this channel, and my goal for this channel is to be a resource for the basic programmer, specifically for the Commodore 64. Whether you're new to the basic language or if you've been programming in BASIC for quite a while, I think you'll find something of interest here. So please like this video and subscribe to my channel, and check out my website, visionbasic.net. I plan to post videos every few weeks, but sometimes more frequently. Alright, so what is this video going to be about? Well, it is not a video about how to 10 print something and then go to line 10. Not at all. My goal for this video is to show you how you can jazz up your basic programs with an attached REU. I have a lot of ground to cover, so this video is going to run longer than intended, so feel free to skip forward to the visual demonstrations if you aren't interested in the informational portions of this video. I'm going to have to read from my notes here to help keep a decent pace, though honestly I'd much rather go with a more impromptu format. I'm running a screensaver of sorts in the background for your enjoyment pleasure, written completely in BASIC, so that I can dish out some dialogue before showing you some sample programs and such. So what is an REU? The letters REU are an acronym for RAM Expansion Unit. It is an external memory add-on for Commodore computers that was introduced in 1986, around the time that the Commodore 128 was also introduced. Early sizes for this expanded memory were 128K, 256K, and 512K. The 256K model was intended for the Commodore 64. It's important to note that a heavy-duty power supply is recommended for use with any of these older REU models on a stock C64. Today, there are REU implementations that go all the way up to 16 megabytes. A lot of people probably think that they are difficult to use, but they're actually not. I mean, programming in and of itself tends to be a challenge, and using an REU is not a whole lot more challenging than poking to the screen or moving a sprite about. What makes an REU stand out compared to other versions of expanded memory is that you can quickly and easily copy large sections of memory back and forth between the Commodore 64 and the REU at blistering speeds. You can pick pretty much whatever memory chunk you want to copy in either device, up to 64K in size, and put it pretty much wherever you want to copy it to in the other device. Now that's the simplified explanation, so let me explain it further. Typically, information is often stashed to the REU and fetched from the REU. The Commodore 128 actually has the commands stash and fetch as part of its command set. There is also a swap command for swapping data between the Commodore 128 and the REU. Sadly, the Commodore 64 has no such commands, but once you have the right routine set up, using the extra RAM isn't all that hard. Unless you add some machine language to the mix, you probably won't want to use your REU to store a large database of text data. But in the area of graphics, an REU could really add some life to your programs. Since Commodore no longer makes REUs, you might be wondering where you can find one. Well, for starters, you'll occasionally see one listed on eBay. I don't recommend paying much more than $100 for one though, since there are some better options beyond that price point. Make sure the seller has tested it before you buy one. But you might actually have one without even knowing it. If you have an Ultimate 2 Plus cartridge, then all you will need to do is to activate the REU emulation. And I've read that previous versions of the cartridge also support REU emulation, but don't quote me on that. So if you have the 1541 Ultimate or the Ultimate 2, you should be able to enable REU emulation as well. Another great option is the C64 by Retro Games, otherwise known as the C64 Maxi. This is a modern replica of the Commodore 64 with preloaded games, but you can access basic mode easily and enable the emulated REU with relative ease. If you have more dollars to spare, you can purchase a Turbo Chameleon 64 or an Ultimate 64. They both have REU emulation that you can enable. And finally, if you have the Vice emulator, which I'm using right now, you can easily enable REU emulation in the menu. You can often leave REU emulation turned on without experiencing compatibility issues with other programs. But if you do experience some problems, just turn the REU off. It's that simple. Also, you can easily max out the REU size to 16 megabytes without any kind of hit to CPU speed. So I say to go ahead and go for the max with whatever version you're able to get your hands on. Okay, so we've established the fact that you can copy data to the REU and copy it back to the C64 when needed. I've also mentioned the speed of transfer, 1 CPU cycle per byte. This is actually quite fast since you can't even move a single byte of C64 memory from one location to another that quickly in machine language. Machine language takes several cycles to perform that same task. So let's talk about how the memory of the REU is laid out. The typical way to look at it is that REU memory is laid out in banks, and each bank runs a total of 65,536 bytes, or 64K per bank. For an analogy here, I'm going to call them pages for a moment, and I'm going to add my own little twist here and saying that each set of 8 pages forms what I would like to call a chapter, which then totals 512K. And I guess the whole REU could be described as a book, if its size is greater than 512K. The reason I'm describing it this way is that you can treat each chapter as one very long section of memory. In this fashion, you can actually use what is termed as long addressing, which is my preferred way to look at REU memory, but you can view it however you wish. With long addressing, 3 consecutive bytes are grouped together to create a value that acts as a pointer instead of the usual 2. You can stick with the usual 64K chunks and treat them as individual banks, or you can view things in terms of chapters consisting of 512K blocks. Either way works. When you copy a chunk of data to the REU at the end of a page/bank, anything that runs past the end of that bank will continue to be copied into the next bank. That is, until you get to the end of the chapter. When you write at the end of the chapter, anything that extends past that page or bank will be wrapped around to the start of the 512K chapter, and data at the beginning of that chapter will be written over. I think this behavior is a result of REU designers not expecting to push these things beyond 512K. So how do you stash and fetch and swap when using an REU attached to your Commodore 64? Well, how do you do pretty much anything significant on a C64? You poke, of course. Essentially, you set your parameters with a series of pokes and then issue a final poke to start the transfer process. Let's take a look at these poke registers. Okay, so as you can see here, addresses 57090 and 57091, these registers point to the start in C64 memory where a transfer is going to take place in low and high format. Next comes 57092 to 57094. These 3 registers point to the start in REU memory where a transfer is going to take place in low and high format and a bank value, which when combined can also be seen as a long address. Next comes 57095 and 57096. These registers represent how many bytes are going to be moved, again in low and high format. A value of 0 here will be treated as a full 64K, which is 65,536 bytes. You'll probably never need to use this value. Next comes register 57098. This register allows you to fix the C64 address or REU address. When you fix an address, it doesn't advance. Typically, this doesn't make sense, but what it allows you to do is to copy an individual byte on one end and fill a bunch of bytes on the other. I'll show you an example of this later in the video. And finally, 57089, this register is what causes the memory transfer to take place. There are several bits in this register that do different things, so the byte you place here will be a combination of values. Let's start with the direction of data transfer. The first couple bits control this. Use a value of 0 to copy memory from the C64 over to the REU. Use a value of 1 to copy memory from the REU back over to the C64. Use a value of 2 to swap memory contents between the REU and the C64. And a value of 3 performs a compare between the two memories. I haven't found a use for this last option, so I'm not going to go into details about it. After choosing one of these 4 options, add a value of 16 to the mix. I'm not going to go into details about what bit number 4 does, so just add the 16. Bit number 5 controls the autoload feature. If the bit is set by adding 32 to our final byte combo, the registers from 57090 to 57096 up here will be reloaded with the values you had initially put into them after the memory transfer has completed. Essentially, they'll remain unchanged after the transfer. If you don't set bit 5, the pointers will each equal the ending addresses of the transfer plus 1. They'll essentially be pointing to the next chunk of memory in both the C64 and the REU. The transfer length will be reduced to a value of 1, though. I personally think it would have been better if the transfer length remained unchanged in this setup, but I wasn't there when they designed this thing. As a note, bit number 6 doesn't do jack squat, and neither do bits 2 and 3 for that matter. Finally, bit 7 is where all the action happens. Add a value of 128 to the mix, poke the whole shebang into 57089, and watch the magic happen. Well, okay, you might not actually be able to literally watch it, but a transfer of memory is what to expect. Alright, so let's load up some routines that you can use in your own programs. You'll definitely want a routine that detects an REU and sees how much RAM it contains. I'm also including a routine to set the REU pointers for memory transfers. Here are some variables that my routines use. Each variable is associated with a specific pointer or address. You can actually poke the addresses directly if you wish, or you can rename the variables if needed. With the pointers, you will need to add a 1 to access the high byte, and you'll need to add a 2 to access the bank byte for the REU. I discussed all of these addresses earlier, so I'm not going to linger here. If you use my routines that I'm about to list, you won't need to poke the addresses pointed to by variables CP, RP, and SZ up here. These are used by the routines themselves. Ignore the variable SR, where is it? Right there. Because the address 57088 that it represents is read-only and is mainly useful for comparing C64 and REU memory, and again, I'm not going to go into that. The variable BF is here and if you intend to specify an area of memory to act as a buffer. Sometimes you might want to specify a good place to pull data in from the REU so that you can analyze it. The memory starting at 49152, which is up here, is a pretty good place to do this. The routines do not actually use this variable. You would need to copy it over to another variable called CA, and I will explain this variable shortly. Or you can poke its contents directly into the C64 base address pointer, right here. The reason to specify such a variable is so that you can easily change it if needed, as opposed to sifting through your program to find the buffer address. The values in line 60 and 70, right here, are the ones you would plug into the address pointed to by the fx variable in line 50, and the values in line 91 to 97, right here, can be combined and plugged into the address pointed to by the variable CR in line 90, but keep in mind that you won't be combining the first 4 values with each other, 0 to 3, just pick one of the 4 values. All of this was explained earlier. Lines 100 and 110 call the routine that checks for an REU and its size, and times how long it takes. You can just delete these lines, but definitely make sure to call the routine at 1000 to detect the actual REU. Okay, so this is the routine you would call to see if an REU is attached to the C64 and to see how much memory it contains. Upon exit, the variable cin will contain the number of banks available. This value can go all the way up to 256 banks, which is the equivalent of having an extra 256 Commodore 64s attached to your machine, as far as memory is concerned. If the value returned is 0, then there is no REU attached, or you have a broken one. This routine first writes values to selected banks, but it's a best practice not to corrupt the data already in the REU by writing values to it. After all, You might exit your program, perhaps by accident, and want to retain the contents of the REU so that you can access the data when you run your program again. So what we're actually doing here in the first part of the program is swapping values with the REU. The values coming from the REU are stored in a safe place while we do our writing test. Because of the order our values are stored into the REU, we can read them back and determine how many pages exist in the attached REU. Lines 1040 to 1070 do the counting. Finally, we need to restore the original values back to the REU that we have written over, so lines 1080 to 1090 perform this task. My entire routine here only takes 2 to 3 seconds to detect the size of an attached REU, which is impressive for BASIC. I saw a similar routine that somebody had published, and their routine took about 13 seconds to perform the same task, so rock on. Okay. You can run this routine while displaying a title screen, and nobody would know that the operation is taking place. And if they don't have an REU, you just halt the program. Or tell them, hey, what's going on here, buddy? Okay. One reason my routine is faster is because there is no reason I'm aware of that you have to check for every single REU bank. This is because REUs tend to come in specific sizes. After detecting for a 128K REU, we can skip forward by 4 banks at a time. I suppose the routine could be modified further to reduce its duration, something I'll look into for a future video. Okay, so this is a routine that you can use to set the pointers and a number of bytes to transfer. You set CA equal to the C64 address and set RA to equal the REU address as a long address. And then you set BC equal to the byte count. These values will be poked into the registers pointed to by the variables CP, RP, and SC. If you don't wish to use long addressing and would rather employ banks instead, you can simply poke the extra high byte of the REU pointer directly, or you can modify the routine with some simple changes. This routine only sets things up for a transfer, so you'll still need to set the register that does the address fixing and then execute the actual transfer by poking to the control register. If you enable the address autoload feature, you can set these addresses a single time and then make small changes to individual registers to help speed things up as far as using BASIC is concerned. Some of my demos I'm about to show you actually do this. And speaking of demos, let's start with the first one. All of my demo programs have the routines I just showed you embedded into them, so that's why the lines up to 97 should look familiar to you. In this demo, I used the sine and cosine functions to draw a crude circle made of character blocks, so lines 100 to 180 make some pre-calculations to help speed up the circle drawing process, since the sine and cosine functions are fairly slow compared to other math operations. You can also draw circles using the circle formula, which is radius squared equals x squared plus y squared. I find this second method a little more complicated to use, so I chose sine and cosine instead. These functions provide repetitive values, so the lines you see here copy repetitive values into the arrays instead of performing sine and cosine calculations for all values. You gotta eliminate wasted cycles where you can when programming in BASIC, right? Here is the part of the program that draws circles on the screen and then saves the screen to the REU every time a circle is drawn. What we're doing here is a kind of page flipping animation that employs the REU for storage. These kinds of programs are more for fun than for any practical use, and you'll often have to wait for all the pages to be drawn before you can view the final animation. Animation in general starts with a lot of behind the scenes kind of work before a final rendering can be viewed. If you want to create longer animations than the ones you're about to see here, you'll have to keep in mind those 512K boundaries in the REU. My animations store exactly 1,000 bytes at a time, but if you wish to avoid issues with lengthy animations, store 1024 bytes per screen, starting starting at byte 0 with the REU, and don't worry about wasting those extra 24 bytes. The same goes with bitmap screens. Just store 8,192 bytes per screen instead of the visible 8,000 bytes. And keep in mind you need to start at the beginning of the REU to make sure that this works properly. I don't recommend storing color screens along with the screen data because you probably won't be able to prevent the potential color flickering that can result, since the color data will likely be restored on a different screen refresh than the screen data. As a side note, I'm not going to explain my programs to detail because this video would then run incredibly long. Since BASIC is generally easy to dissect, just analyze the code yourself. It's one of the best ways to learn BASIC. Do notice that in line 200, though, that we are calling the REU detection routine that starts at line 1000, right here. And notice that in line 270 that we are calling the routine starting at 2000 that sets the pointers for transfer. So the second poke in line 280, right here, is what causes the screen data to get stashed to the REU. You'll notice that I have different values being added together in that poke statement. This can help remind you what kind of transfer is taking place, but the extra math there can come at a cost in speed for some situations. If speed is important, consider adding the values together. You can always add a rem statement explaining what the poke value actually does. And here is where the animation playback happens. The first half of the routine performs some pre-calculations for low and high values to help make the animation playback faster. The second half actually does the animating. Okay, let's run it. What you'll see here in a minute is the frame drawing process followed by the actual finished animation being played back. This animation consists of 38 frames and takes up 38,000 bytes. So technically, it could fit within the Commodore memory, but you couldn't play it back at a decent speed without the aid of machine language. By using an REU, we bypass the need to use machine language entirely. The end result is something akin to a spinning coin animation. Let's wait for it. Okay. So it's kind of simple and lacks 3D depth, and it's kind of chunky, but it's still pretty impressive for BASIC, I mean, when you consider the speed. Okay, let's stop it. Oops. And here I just wanted to show you how I put some variables up at the front of the program. In doing so, these variables get fetched more quickly, and it helps to speed up some calculations in the program. The 0.5 that you see here added to the p variable helps with accuracy. See, if you add a tiny negative fraction to a whole number, it will immediately decrease the whole number by 1 as far as positioning is concerned on the screen. But adding a fraction to a whole number won't change the visible positioning of the coordinate at all. And it can create some problems, or some inequalities there visibly. So the 0.5 helps to balance things a little. Just trust me on it. Okay, let's move on to an improved version of this demo. This is a modified version of the previous demo. If we list the first line, we notice that it hasn't changed. And if you're wondering why I don't type list 0, well, that's because it'll list the whole program. So I'm trying to prevent that. So list through 1 actually does the job. So, and next, list 180 through 180. Okay, here we have some calculations and some differences compared to the original program. Again, due to time constraints, I'm not going to go into extensive details. Just look it over in your spare time. Here we've modified the code to include some calculations to give the appearance of 3D. So notice the z coordinates in line 240, right here and right here. And again, we have our REU high and low pre-calculations, and we display our animation. And we're going to skip some lines here for a minute. Here we are filling the screen with colored spaces ahead of the animation so that whatever is animated to the text screen will already be colored when we animate things via the REU. Unlike printed characters, bringing in text data from the REU doesn't change what's in the color RAM. So it's a good idea to actually print the color first before animating. So before going too much further in describing the program changes, let's go ahead and run the program and see what happens. Okay, this demo takes about 12 or 13 minutes to draw all 38 frames. So we're going to put Vice into warp mode here and minimize the screen so that it can finish faster. As you may have surmised, we are using a medium resolution of sorts, employing characters that are already a part of the Commodore character set. And we'll give it a second here. And voila, okay, it's done. Disable warp mode. Okay, now all I have to do is press a key. And voila. Now for basic, this is pretty impressive, I would like to say. Tooting my own horn. The 3D aspect makes it look like the loop is swaying side to side a little bit. The gray color bands that I had it print before animating give it a metallic finish. You are getting sleepy. Well, that's not a good thing to say. I hope not. Okay. Let's go ahead and stop it. Okay. Boop. Let's list more of the program. Okay. In BASIC, you need to speed things up where you can. So when it comes to drawing in medium resolution, it helps to set up an array that contains helpful data. I'm not going to explain all of this to detail, but the characters containing the medium resolution patterns are stored at the beginning of the array, and on top of that, specific elements of the array are filled with binary dot patterns. This is evident in lines 3010 and all the way to 3050. The array serves a dual purpose and is used in two completely different and reversed ways. The routine that utilizes this data array is here. This routine draws a medium res dot, or here I call it low res. Yeah, I confuse myself on whether or not these dots are really low res or medium res or whatever res, but they're surely not high res. I guess the lowest res would be a reversed space character. I don't know. Anyhow, despite the confusion, a position on the text screen is first calculated, right here, and then a bit pattern is defined in the next line. And finally, the bit pattern is combined with the existing bit pattern already on the screen and then poked back, right here. Okay, so I created a further version of this demo because I wanted to see if I could eliminate that subtle side-to-side movement, and so let's load it. Oops. And run it. And again, we are going to put Vice into warp mode and minimize the window. This demo takes about twice as long to draw everything, about 24 minutes to draw all 38 frames. Again, keep in mind that making page flipping animations just like this is just for fun. If you are using BASIC, there is going to be a waiting time for sure. The Vice emulator can certainly cut the waiting time down. The speeds you can attain with Vice in warp mode depend on which version you are using and what kind of processor your PC has. And let's see where it's at. Okay, voila. I'm pretty good with that warp mode. Okay. And let's press a key to get it going. Now we have two metallic rings rotating about a center axis. One is circular and one is oval or elliptical. It doesn't matter how much stuff you cram onto the screen or how complicated you make it, it's going to play back at the same rate, which is kind of a cool thing. Again, also especially for BASIC, so have fun with this kind of stuff if you like to make animations and such. Alright, we're going to move on to some other ways that your BASIC programs can benefit from an REU. and we're going to run it. Now I'm going to show you three demos. This first one shows you how you can use an REU to preserve a background so that you can summon up a pop-up window and restore things when the window disappears. In this example, I have limited things to a single text color. You can try to save the color data to the REU along with the text, but the transition between making the window appear and also making it disappear will likely introduce an undesired flicker effect. In this demo, I can move the window around as if dragging it across the screen with a mouse, like on a modern PC. Before the window is introduced, we first preserve the background by copying it to the REU. We only need to do this once. Next, we change where the text is drawn to an invisible screen per se. This is done by poking the appropriate value to location 648. In this case, I've moved the invisible text screen to location 49152. The screen you visibly see now is still located at location 1024. So what we do next is copy our saved background to this invisible screen and draw our pop-up window on it, because printing has been diverted to memory starting at 49152. Once the window is drawn, we copy this invisible screen to a second slot in the REU and copy it back to the visible screen, since we can't directly copy the invisible screen to the visible one without the help of machine language. This technique works well if you want to be able to move printed objects around the screen. You can create a game using this technique, like drawing a flying craft or using graphics characters, for example. Technically, this triple screen swap is faster than using machine language to accomplish the same task. The part that slows things down the most is the printing. And obviously, drawing larger areas of text is going to take longer than drawing smaller text-based objects. So I've actually tested this. Yeah, if you just draw like a little tiny thing, yeah, it's going to be a lot quicker. If you don't need a moving menu, you can simply copy the screen to the REU, draw the menu window on the regular text screen, and then restore the saved screen in the REU back to the text screen memory when you wish to eliminate the menu. I hope you got all that. By the way, when you move text printing by changing the value at 648, you'll want to change it back to point to the regular text screen as soon as you can. If your program crashes or if you stop your program in the middle, your computer may seem unresponsive. Even run stop restore won't bring the cursor back. In this case, your text printing is still being diverted to an invisible screen. So to fix this, clear the screen, even though it won't visibly, use the clear character. Do that first, and then blindly type poke 648, 4, and press return. This usually does the trick. The value you poke to location 648 is the screen location you want to print to, divided by 256. You should keep to multiples of 1024, otherwise crashes could occur. And I know that as a fact. Okay, so let's move on to the next demo. This demonstration shows you how you can use an REU to create a horizontal scroll. Essentially, we are saving the screen to the REU and then shifting it all left a single byte when we restore it to the screen from the REU. Because a wraparound occurs on the right-hand side over here, we need to draw new content down the vertical strip of characters that runs down the right-hand side. The number of visible columns have been reduced to 38 columns, so that we don't see the new characters being drawn on this right-hand side. Otherwise, you'll just have a kind of flickering effect. Since almost 100 characters are being drawn, this again slows things down a bit. If we were only performing the REU transfers, the movement would be much faster. And again, the colors were drawn to the screen ahead of time. If you are wondering why almost 100 characters need to be drawn for a vertical strip of 25 characters tall, you would need to understand that 2 cursor movements need to accompany each character, and in this particular example, a reverse on or off character is also issued. If we were to turn this into a game, we might put in a biplane on the left side over here of the screen, and have him shoot at approaching targets on the right over here. Vertical scrolls are also easy to perform using an REU, and BASIC doesn't natively support a downward screen scroll. And now I'm going to move on to the last demo of this trio. As we watch the progress strip run down the screen, this demonstration shows how we can swap color in from the REU to create a stunning visual effect. And voila! I think it's pretty impressive, don't you? You can use this effect for a title screen, but it's best to have plenty of characters on the screen. I tried putting a simple 4 or 5 character tall title in the middle of the screen and the results just weren't that impressive. And when you stop the movement, it kind of loses the jazziness. So keep it moving. Okay, we're going to list some stuff here. This part of the program preps things for the color dip bar demo you've just witnessed. All the rows of color are outlined in the data statements up here. There are a total of 66 rows of color, and we print the color bars invisibly to the screen at 22 rows at a time. This is done 3 times, and each time we store those 22 rows to the REU end to end, thus creating a color screen 66 rows tall. When we are ready to animate, our starting point is at the top of this tall wall of color, and we only restore 25 rows to the color RAM at a time, and we scroll our way down within the REU itself 40 characters at a time. Line 880 draws the maze-like background for the demo, this demo, and get back to those, okay. And again, we put variable P at the top of our program to help speed up this maze drawing procedure, which I'll list again, as you can see right here, because it's 1,000 characters, so yeah. And here's the part of the program that actually animates the color bars. We only scroll down from rows 0 to 39 out of the 66 available rows because going further will only start to dredge up garbage bytes past the end of the 66 rows stored in the REU. A row or two of the total 66 rows might not even be drawn. Yeah, my program is a tiny bit sloppy, forgive me. Anyhow, feel free to use this effect if you'd like in your own programs. Let's go back to the other 2 demos we saw and look at some lines. This is our menu window demo from earlier. The first half draws the background. A trick is used in line 130 up here. That pushes the last character into the corner to help avoid a scroll up on the last line. The second half crams all the character data for the menu window into a single string for speed. In line 290, we are moving our printed text screen to start printing at location 49152. And that's what the 192 is for. So if you could type, if you multiply it by 256, oops, sorry. Oops. Let's try this over. Okay, there you go. Sorry. We get the where our screen's located. Okay. Blah, blah, blah. I'm messing up here. All right, forgive me. We're going to list further stuff. I might keep this in for humor. I don't know. Okay, this part of the program prints the menu window to the hidden screen at 49152. I chose to have the right lower corner of the menu window poked instead of printing it to help prevent scrolling when the menu is down in the lower right corner of the screen. So right here you can see this poke. I used a technique of chained if-thens to speed up the cursor control of the menu window. So what happens here is we're doing if-then statements, and if the condition is not true for any of these, then the second half isn't even executed, which helps to speed things up a little bit. Do everything you can in BASIC to speed things up. I mean, unless you like slow stuff. So anyhow. Okay, this is the part of the program where memory is transferred between the C64 and the REU. Again, 3 transfers take place here. So to recap what is happening here, we are copying our save screen from the REU to location 49152. Then, once we print our window, we copy the screen at 49152 into the another slot in the REU, and then we copy that slot into the C64 screen at 1024. Try to keep up, folks. Okay. And I'd like to apologize if you're not like that far advanced into BASIC and stuff like that. I'd recommend getting, a book, a memory map of the C64, and it'll work wonders as far as helping you to learn stuff you might not know. Okay, moving on to the horizontal scrolling mountain demo. Say that 5 times fast. The first few lines here set up the strings that draw the mountains. Lines 680 and 690 print out the white and brown colors for the mountains. Right there. And line 694 turns on 38 column mode. And this is the part of the program that animates the mountain range. Lines 730 and 740 shift the screen by a single byte. Notice the goes up in line 700 right here. We're going to list that. And this is the part of the program that sets defaults for the REU pointers and such, so that the program will be able to get away with fewer pokes to issue an REU transfer. If you look back at lines 730 and 740 up here, you'll notice that it only takes 2 pokes to issue a single REU transfer once all of the defaults are set. This is one of the main reasons to enable the autoload feature, or the autoload option, in the command register. Now I'm going to show you how you can benefit from using the fixed address setting. Alright, this is a bitmap screen, believe it or not. Notice all of the garbage data. Now we're going to completely clear this bitmap screen entirely from BASIC with no help from machine language. Not a lick. Bam! The entire screen cleared in an instant. How can this be, you might ask? Well, by using a fixed address, we can copy a single byte over to the REU and have it copied back to the 8,000 bytes of the bitmap screen and also the 1,000 bytes of the bitmap's color map. We only need to fix the REU address to do this. Once the REU pointer is set, it won't change. A single byte from the REU gets copied again and again and again and again. Next, we are going to use the same technique to fill the entire bitmap screen with the byte value of 255, and next the value of 254, and next the value of 253, and further down until we reach 0. And again, there will be no machine language trickery. This is simply a speed test. So here we go. Be amazed. I wish I had music for this, but alright, and now the program is performing a calculation. Essentially the same basic routine is being run without actually issuing any REU transfers. We can subtract the time lapse of one from the other to determine how long it takes for only the REU portion to happen. Okay, the stats here show how long it takes to clear a bitmap screen just one time. The first 2 stats include the basic portion of the process, and the last statistic shows how long it takes without the basic overhead. So up here you can see that it takes 0.044 seconds, which is equivalent of 2.6 jiffies to clear the bitmap a single time. And then if you just count the REU portion, no basic, it takes less than a single jiffy. So the REU part of the process takes less time than a single screen refresh. You just can't get those results from machine language, folks. So, if you want a quick way of clearing a bitmap screen, consider using your REU. Alright, so let's take a look at the code real quick. Here we are lowering the top of memory down to 23552. This is where the color map of the bitmap screen goes. The bitmap itself is only 1K beyond this point, starting at location 24576. Lines 110 to 150 fill the bitmap screen with noise from the Commodore sound chip. We first fix the C64 pointer and have it point to what they call the random number generator at location 54299. We copy this generator 9,216 times into the REU. Then we copy all 9,216 bytes back into the bitmap and color screens from the REU, first making sure that the C64 pointer is no longer fixed. Lines 160 to 190 actually make the bitmap screen visible with all the appropriate pokes. And again, consult the memory map to help you figure out this kind of stuff. I'm not going to explain it. I chose this location because, to the best of my knowledge, this is the highest place I think you can easily place a bitmap screen for basic use. Okay, line 200 alone here clears the bitmap screen with calls to routines starting at lines 3000 and 4000. Lines 220 to 260 are where we fill the bitmap screen with values from 255 down to 0. Lines 300 to 340 perform the mock fill I told you about, where REU transfers don't actually take place. All we need to do there is to poke benign values into the control register. So as you can see here, these are benign values. They won't do anything. And lines 400 to 440 restore a normal text screen, and then the stats are displayed down here. And these are the routines that clear the color screen and bitmap screen. To keep these routines simple, I just have them poke each screen with a single byte of data and then copy that byte to the REU. Then I have them copy the byte back to the same exact spot, but this time that single byte gets copied back multiple times until the appropriate screen has been cleared. Again, this works because we fix the REU address. With high-res bitmaps, each 8x8 square gets a plotting color and a background color. So variable C should contain the plotting color and variable BG should contain the background color, both before calling the routine. And now we reach the end of the video. So as you can see, there are several cool things you can do with an REU with BASIC alone. I personally think that they are highly underutilized, and, well, I guess I'd like to help change that. If you've ever done anything kind of cool with an REU in BASIC, go ahead and post it in the comments. I thank you for making it this far through the video. I know it's kind of long. Hopefully future videos won't be as long. And again, please like and subscribe to my channel for more content on programming the C64.